So I'll introduce our first speaker for today is Ron Erel. Ron is a member of the Department of Soil Chemistry, Plant Nutrition, and Microbiology for the Institute of Soil, Water, and Environment. He works for the Agricultural Research Organization at the Volcani Center in Israel, and he's based at the Galat, I hope I'm pronouncing that right, Research Center. Ron's research interests focus on root-soil interactions, and his lab is focused on three major aspects of plant nutrition: development of enhanced fertilization strategies for fruit trees, phosphorus acquisition by roots and soil chemical processes affecting phosphorus bioavailability, and environmental and physiological factors governing calcium allocation to fruits, which is a very important topic for avocados. So with that, I'll turn it over to Ron. Thank you.
Thank you, Mary Lou. I will share my presentation. I've been working for a very long time on olive nutrition. This is where I did my PhD. So avocado is pretty new to me. We have been working, we is a group in Gilat, a multidisciplinary group working on aspect of irrigation, physiology, pollination, and myself plant nutrition in the past 5 years or so. Of course, avocado is a big deal in Israel, and plantation expanding rapidly. There's good prices in Europe, and currently over 50% of the product is export, mostly to the EU. So it's a bit different than California. When I said we've been working, it's more than just a single or couple of experiments. It's a project. When we have controlled experiment where we grow the avocados in containers, something we did in many fruit trees, and give us a lot of information, and I will share some of it with you. And when we found a question that we can directly go to the field and ask, for example, what calcium does to post-harvest quality, and I will share with you some of the experiment we are doing also in the field, all of course associated with plant nutrition. Now, it's a big topic, and 30 minutes I decided to talk about nitrogen, because nitrogen is the key. It's the key for plant development, it's key for plant productivity, and also for post-harvest quality. So we will look about how the avocado acquire nitrogen at different phenological stages. This is the first aspect that I'm going to present. Later, I will present the challenge of accurate diagnosis of nitrogen level in the avocado. And this is a challenge. And later, we'll see what's variate availability of nitrogen, how it's affected the post-harvest quality of avocado. All the work that I've been doing is on the Haas variety. This is the most important variety in Israel, and this is what we are focused on. So to learn about the annual dynamic of nitrogen acquisition, we established a platform where we grow the avocados in large containers. This is 1 cubic meter container filled with perlite substrate. So it's completely inert. The trees or the roots are exposed directly to the concentration that we give. And we have 5 concentrations of nitrogen from very low, approximately 10 milligram per liter, in every irrigation, every day, all year long. 20, 40, up to 120 milligram per liter, where the 40 is the average. Okay, this is what you'll find in the common Israeli farmer, okay, will be around 40 milligram per liter, okay? We manipulate nitrogen, but phosphorus, potassium, micronutrients, everything else is fixed. So only nitrogen. In our case, I will present the results only from the nitrogen. We also manipulate phosphorus, potassium, but this is a different story. So this is how we started almost 5 years ago. This is how the platforms looks like now. So we have big, healthy, productive trees, nearly 5 years old, starting full production last year. We monitor, we do a mass balance of water. So we have, for each container, we have the water, the daily water uptake, 365 days a year. And we simply do it by measuring the irrigation volume by very accurate water meter, and later the drainage is being collected in these green buckets, and by gravity goes down to a weighing station where during the night each tree, the drainage of each tree is weighted and recorded in this data logger. And of course nowadays everything is sent to the clouds and collected, and you can see that the postdoc that worked with us developed an app, and we can see the water uptake of each tree, each day, and so on. Now, when we do mass balance of water, we can also manually sample the irrigation water and the drainage water, take it to the lab, and do mass balance for nitrogen, for phosphorus, for potassium, and so on. So the amount of nutrients that we apply in the irrigation is measured every 2 weeks or so, and the amount of nutrients that we found in the drainage is measured simultaneously. So if we applied 5 grams of nitrogen and we found 2 grams in the drainage, we can calculate the uptake of nutrients. This is not continuous because we collect it, manually, but we do it roughly every couple of weeks. So this is how the water uptake dynamic as affected by N level looks like. First year, second year, third year, and now we have the fourth and almost the fifth year. And you can see, for example, the low nitrogen, it started low at the summer of the first year, and now the water uptake is very, very low. Of course, it's very small tree, and you can see the N80 indicating 80 milligram per liter is the biggest tree throughout the experiment, reaching very high water uptake during the summer. Okay, this is how a typical day in the summer looks like. So the more nitrogen we apply, the higher the evapotranspiration is, the daily evapotranspiration. This is from August last year. And of course, this is indicating the tree size. The bigger the tree is, the higher the water uptake will be. So we can see that avocado responding tremendously to nitrogen. The more nitrogen we gave, up to 80 milligram per liter, we got bigger tree, bigger truck. By the way, the LAI, everything we measured was bigger. And then when we increased nitrogen from 80 to 120 milligram per liter, we have huge decrease in the tree biomass, indicating some kind of nutritional disorder or over-fertilization. You might say toxicity, but we don't see any toxicity symptoms. The salinity of the irrigation water is still very low, around 1 decisiemens per meter. This is something else. This is nutritional disorder. And as I said, we do mass balance for water and we do mass balance for nitrogen. Here, just to illustrate, I am presenting the nitrogen concentration in the drainage for 3 years of experiment, okay? So we apply, this is only for the and 40 for the treatments that receive continuously 40 milligram per liter, and the concentration is indicated in the dashed line. And we measure in the drainage. So you can see that in summer 2019, the concentration in the drainage and the concentration in irrigation was similar, and then it increased back, decreasing, increasing, decreasing, and so on. That shows that there is some kind of annual dynamic to the nutrient uptake. In the summer, there are excess of nitrogen. We supply more nitrogen than the tree consumes, and that's why the concentration in the drainage is higher than what we supply. The water uptake exceeding the nitrogen uptake. In the winter, we have the exact reverse trend. Well, actually, in most of cases, in winter, we didn't find nitrogen in the drainage. When I said winter, it's between December to February, okay? What we consider some kind of dormancy. You don't see in Israeli climate, you don't see anything on the trees. And mostly we thought that the nitrogen uptake will be very, very low. But we see the exact opposite. Nitrogen uptake is exceeding in the winter, where there's no growth, there's nothing visually. So my colleague Or Sperling, he took the data from avocado and almond and pomegranate, and he did this some kind of mathematical manipulation to quantify or to optimize the right concentration at different phenological stages. So you can see that in avocado, as I presented, there is this annual dynamic where it's very low in the winter and high in the summer and so on. That was true also for phosphorus, but you can see here in almond, for example, in a similar platform, most of the year he was way, way over the optimum, okay? So eventually what he came up with is some kind of recommendation. It's being published in Irrigation Science, where you can see that in summer, the concentration of nitrogen should be lower, partly because the amount is higher, partly because the demand is lower, and in the winter we should have higher demand for nitrogen. So we took this very surprising information into the field, and for 2 years we supplied 50 kilogram per hectare. You should convert it to pound per acre. Too much for me now. Since during the winter we have significant precipitations here, January, February, March. So we thought that it will be wise to stick with ammonium as source of nitrogen. So we had treatments where we supplied ammonium or ammonium with nitrification inhibitor, or uran is a mixture of urea and ammonium nitrate. We supplied it for 2 years and monitored the yield. And what you can see, basically, this is after 2 years, we have an average increase of 2.7 tons per hectare, which is significant when we supplied nitrogen in the winter, okay? The only manipulation we did is adding 60 kilogram of nitrogen per hectare during the winter time. It doesn't matter what source of nitrogen we supplied. Wherever we supplied, we got an increase in the yield. So currently, my recommendation to the farmers, and gladly most of them adopt it, is to take about 1/3 of the nitrogen dose, the annual nitrogen dose, and supply it in the winter. And you should take from the summer and put it in winter. For Israeli farmers that don't irrigate, during the winter and supply nitrogen only by fertigation. That was really difficult to adapt. But after we saw it both in the controlled experiment and then in the field, more and more farmers adopt this practice. The second issue I would like to present is the challenge of accurate diagnosis of the nitrogen level. Because of course, different rootstocks, different water sources, different soil type and soil fertility, some applying manure, we cannot have a single number of how much nitrogen is needed. And I saw the calculator. You can calculate very precisely how much nitrogen you removed, but it's not that easy to estimate the amount of nitrogen needed for the new vegetative development. And avocado grows, it's very, very vigorous plant species. So at first stage, we wanted to replace the old-fashioned wet chemistry diagram that you see here, that is time-consuming and expensive, and we simply replaced it with NIR. And what you can see here is not calibration, it's validation. Again, I did it with my colleagues at the Gilat Research Center, Uri Yirmiyahu and Or Sperling, and they got all the thousands of leaves that I analyzed the old-fashioned way. They created calibration, and then I gave them 50 samples that are blank, that were never used in the model, and you can see the excellent agreement between the near and content and the old-fashioned wet chemistry and content. So currently we are using mostly the near. We also added some kind of auto sampler. So this instrument can measure a few hundreds of leaf samples a day with only one technician, which is 10 times more than the old-fashioned way. And this enables us to have more leaf analysis for less money. And this is very important stage in order for accurate diagnosis. Of course, the next stage is using drones and so I'm also collaborating with a remote sensing researcher. This is Tarin Paz-Kagan from Ben-Gurion University. And I must say it doesn't replace the leaf analysis. It can show variability. It can show where not enough nitrogen is supplied in the orchard, but it's absolutely not the standard tissue analysis. Okay, but when we look at 20 hectares of orchards, we do see variability, and this is very important for the farmer. But this is not what I want to talk about today. Mostly, I want to focus on the nitrogen over-fertilization, because nitrogen deficiencies in modern developed agrosystem, it's very rare. Farmers supply nitrogen. There's no question. The question is it enough or too much? Mostly, you don't see much deficiencies, yellowish pale, retarded trees. You mostly see very big green trees, but as I presented you earlier, when you exceed the optimum, there is a sharp decrease in the tree performance. It's still green, it's still nice looking, but it's much, much smaller. And of course, the potential to bear yield significantly decreases as well. So how can we diagnose it? And this is, again, just for illustration, similar platform in mangoes, and you can see that nitrogen over-fertilization, not only deficiency, also nitrogen over-fertilization significantly reduces yield. That was published by our colleagues Avner and Uri Ochberg recently. So again, just for illustration, you see here young trees where we supplied low level of nitrogen. The tree is small and yellowish, chlorotic. When we supply the nearly optimal level of nitrogen, you see that it's much bigger and greener, and this is over-fertilization. The tree is very green, look very vital, but it's significantly smaller. You can see that the water uptake significantly decreases 2 months after exposure to nitrogen over-fertilization. So how can we diagnose this over-fertilization? One would say, let's look at leaf analysis. But leaf analysis is excellent in detecting deficiencies. You see that this small chlorotic tree has significantly lower N level in the leaf compared to the well-supplied trees. But the over-fertilization is not manifested in the standard leaf analysis. It simply reaches some kind of a plateau. And you can see here the nitrogen level and the leaf analysis. You can see the low nitrogen is below the deficiency threshold. And earlier I was told that your threshold is somewhere around 2.5. But this is the optimum, okay? And we get exact same N levels as we get in the over-fertilization. You cannot detect over-fertilization with the standard leaf analysis. And this is also true for almond. This is 150 actually caused the death of almonds, and still the leaf analysis is not exceeding the optimum, and pomegranate and olive and so on. So this is something that is common for all fruit trees, not only avocado. And we invested a lot of effort in finding another metabolite. We thought that amino acids will increase very much when the trees will be over-fertilized. We monitored for 3 years, and well, at the beginning, it seems to be working, but it's changing from season to season, from year to year. We couldn't identify one specific metabolite or indicator for nitrogen over-fertilization, and so far we are facing some kind of dead end. The third and the last topic I want to talk about is the effect of nitrogen on fruit quality. So one very basic fruit quality parameter is the fruit size. And you can see here the average fruit size from the controlled experiment. And you can see it's also acting in kind of optimum curve. It's very low when nitrogen is deficient. It's increasing to an optimum at 80 milligram per liter. And then there's a sharp decrease when nitrogen is fertilized in excess. We also saw it in the field. So these are trees that were not fertilized. We used recycled wastewater, so there's quite a lot of nitrogen there. 250 kilogram nitrogen per hectare. This is the standard in Israel, and 600 kilogram of nitrogen per hectare. And again, you see that nitrogen over-fertilization at 2020 off year or 2021 on year, both significantly reduced the fruit size, and of course that have economic implications. Now, next we looked at the internal gray symptom. Maybe I should have started with this, okay? So the internal gray pulp or internal discoloration is the most common post-harvest problem in Israel, mostly because the fruit is exported. So it needs to be 3 weeks in the ship and then another week on the shelf. And this is how it looks like, healthy fruits. And this is very fruit that has very big damage. Okay, so this is what we see here. And again, 2029 one, we saw this same optimum like response curve, that nitrogen deficiency and nitrogen excess had the worst post-harvest quality. And then in the middle, we get fair to good post-harvest quality. I will talk about nitrogen deficiency later. The next season, it's not 2002, it's 2022. We assigned Dr. Noam Elkan, which is a specialist in post-harvest. And what we found is a continuous decrease in the post-harvest quality or continuous increase in the internal gray pulp symptom with nitrogen. The more nitrogen we applied, again, the fruit looks perfect at harvest. After 3 weeks, it has a lot of internal gray. Now we go to the field and we see exactly the same. Nitrogen deficiency, we have very high rate of internal gray disorder. At optimum, again, this is 200 kilogram per hectare. This is the practice in Israel. We have significant reduction, and again, nitrogen over-fertilization significantly accelerate the occurrence of internal gray symptoms and the severity. And you can see it here, but what Noam noticed, and I couldn't, that the nitrogen starvation and nitrogen over-fertilization, it looks the same, but it's different phenomena. If you look at the fruit, so let's look at the fruit closer. Here you see the discoloration occurs in the veins, okay? It looks much different than the nitrogen over-fertilization. This is the classic appearance of internal gray symptoms. It starts from the bottom at the opposite side from the branch next to the pit, and not like this. And eventually, Noam concluded that this is actually chilling injuries, and this is the classical internal gray pulp symptom. And what happens in one of the years, temperature dropped around 0 before harvest. And what we saw is that the fruit at the low nitrogen treatment, all of it turned reddish. This is not the classical black skin of the husk. It actually turns red. And this another, again, a symptoms of chilling injuries. So let me summarize. Low nitrogen availability, we can easily get chilling injuries. Excessive nitrogen availability, we get the classical internal gray pulp symptom. Now, the post-harvest quality is a big deal in Israeli exports. So we did a field survey. We went to 11 different sites all across Israel. We took fruits with and without internal gray, and then we did mineral analysis. And for sure, you won't be surprised to see that there's good correlation between calcium in the flesh and the incidence of internal gray pulp. So fruit with high calcium level has less chances to have the internal gray pulp than fruit with low calcium level. Okay, but the site was very significant factor. So we cannot say that at a single calcium rate, it's completely safe and vice versa. No, each site behave a little bit different. And of course, calcium is the main candidate for post-harvest quality or internal fruit quality, because we know that calcium builds the structure of the plant tissue. The cell wall is built of fibers, and the calcium is the cement. And if there's not enough calcium, the cell wall is not strong enough. And then it breaks. And we have in vegetables the blossom endrol, in pepper and tomato. This is not a disease, it's calcium deficiency or disorder. And in mango, we have the jelly seed, and in apple, we have the bitter pit. So these are all physiological disorders that related to low calcium supply. Now calcium is a big, it's very unique in the way that it's only mobile in the xylem and it's immobile in the phloem. So fruit, or in general, non-transpiring organs, has very, very low calcium concentration. But about avocado, there's a lot of statements in literature, not as much solid scientific data that's showing the importance of calcium in the internal gray pulp. And what Noam did at first stage is simply dipped the fruit after harvest with different calcium sources, and he showed that he can significantly reduce the incidence of internal gray by increasing the concentration of calcium. Again, he did it post-harvest. The farmers didn't like it. Nobody wants another stage in the harvest process. And we were looking at other alternatives. Now, I've showed you earlier that nitrogen has a tremendous negative impact on post-harvest quality. And now maybe we can understand it, because we see that nitrogen and calcium are antagonists. The more nitrogen we found in the fruit, the less calcium we find in the fruit. And here, these dots are assembly of two field experiment and the pot experiments. And you see that it's very, very solid, very robust, inverse correlation. When we increase nitrogen, we decrease calcium. When we decrease calcium, we have lower quality of the fruit after harvest. Another very important parameter, nitrogen is not the only one, for sure. There are many others. And one of them is the fruit load. In general, big fruits tend to have low calcium concentration, and small fruits has high calcium concentration. When I ask the exporters, do you know if the internal gray symptoms happens more in big or small fruits? They said, of course. Big fruits are more susceptible to the internal gray, to this decay. So now we can explain it. Big fruits has less calcium. And why we have big fruits and small fruits? It's mostly fruit load. When trees has very high fruit load, okay, then it has small fruits. And when it has small fruits, the calcium concentration is high. Where the fruit load is very low, about 10 kilograms per tree, then the fruits are very big, and thus the calcium concentration is low. So if you want to have high quality of fruit in a post-harvest, you need high fruit load. Okay, so that's how we solve the the challenge. Yeah, I'm joking, of course. After understanding that calcium is central and calcium and nitrogen are antagonists, we thought, can we increase the calcium concentration in the pulp? And this is very tricky. Again, it's not obvious. We grow all of our avocados on highly calcareous soils where calcium should be, the bioavailability of calcium is very, very high. It's very high. It simply goes to the leaf instead of to the fruit. But let's say if we want, when is the best time to apply calcium? And again, here I repeat a work that was published elsewhere. And you can see again that This is the calcium accumulation, how many milligrams of calcium accumulates during the growing season. And you can see that during the summer, this is where the fruit takes most of its calcium. In the winter, there's hardly any difference in calcium content, not concentration. Concentration is continuously decreasing because the fruits accumulate oil, accumulate solids in general, but it doesn't accumulate calcium during ripening. The calcium from October to December, the change is zero. Okay, so the concentration decreases. But when it accumulates most of the calcium, that happens July, August. So on spring, about 25% of the calcium is acquired to the fruit, and then summer about 50%, and autumn the remaining 25%, roughly. Okay, that's not the case for other nutrients. For example, phosphorus, potassium, it all accumulates linearly. It also accumulates during the winter time. And you can see, just for comparison, earlier Mary Lou showed you the tremendous amount of potassium that is being removed. So you can see that at harvest, a single fruit contains about 500 milligrams of potassium, but hardly 15 milligrams of calcium, okay? Just to show you how little the amount of calcium in the fruit is. And this is because of mobility rather than availability, limitation of mobility. So overall, to conclude, we saw that more nitrogen leads to less calcium in the flesh. Low fruit yield leads to large fruits and again less calcium, and this eventually leading to decay in the post-harvest quality of the avocados. And when we used what was recommended in the literature, the N to calcium ratio, we see that it well correlates with the post-harvest quality of the avocado. And what we've been doing in the past year is trying to find a way to increase the calcium concentration in the fruit. And this is, again, this is very, very tricky because the problem is not availability, but it's mobility. And we won't open it here because that's a whole different story for a different talk. But we think we have a way to supply more calcium during the season. We are doing it with mangoes for the reason to decrease jelly seed, and we succeed in that. We are doing it in apple to decrease the incidence of bitter pit. And now we are trying to do that in avocado. This is the first year, so I have nothing to show you. But I think it's feasible to slightly, to some extent, to increase the calcium concentration using the right fertigation complex. And again, it's not an easy thing to explain. And we just started to do that in avocado last year, so we'll have some results next year, hopefully. That's it, and I will conclude that this work was done with a lot of collaborators and was funded by the Israeli Avocado Board and the Israeli Chief of Science, and partly also by ICL. That's it, and I'm available for questions if you have.
Thank you, Ron, for a great talk. We had two questions. I think before we go to Rob, we'll just ask us two questions. One was, how did you decide how much water to give each tree?
Okay. I assume that you mean in the large containers.
Yes.
So what we do, we apply the amount of water that will lead to 30% drainage. So every day we get the volume of drainage and we manipulate the irrigation so to get 30% drainage. So if daily water uptake is 100 liter, the irrigation will be 130 and so on. In the field, we simply follow the recommendation of the extension services.
Okay, and then the other question was that gap between 80 milligrams per liter versus 120 is huge. So the question was, are you looking at that large range to sort of fine tune it, that it drops off at 100 or 90 or whatever?
Yeah, no, we are not doing that. It's a lot of effort. It will take years. It's fruit trees. You cannot ask too much questions. But I disagree. It's not huge. It's another 40 milligram per liter. It's not very big difference. Okay. For example, the difference between 40 and 80 is marginal. And the difference between 80 and 120 is the same, but it has huge negative impact. So this is some kind of physiological disorder that I cannot really put my finger on.
Yeah, so for those that are on the call, I mean, what Ron has shown us has been verified around the world on the effect of excessive nitrogen on fruit quality. And but this data set is very, very nice. I mean, everybody knows that I'm very interested in post-harvest, and I've done a lot of work on post-harvest, and this data set is very, very nice, and it strengthens the literature we have from around the world, from South Africa, from Mexico, from California, from Australia, that you know, you're not only wasting money when you over-fertilize, you're affecting the quality of your fruit. And we can get away with it in California because we don't export our fruit. But if we ever started exporting fruit on a large scale, we have to be very mindful of what was shown to us today. One other question just came in. Have you seen more fibers or strings in fruit with a high nitrogen?
No, there are other defects, like bruises and so on. I think it's all related to the very low calcium concentration in the fruit supplied with high nitrogen level. So in total, we call it decay. The different symptoms, not fibers. No.
Yeah, and is it more difficult to over-fertilize with nitrogen if you're an organic grower?
I think that mostly they have the problem with not enough nitrogen and over fertilization with phosphorus and potassium. Because when you use manure or compost, you don't supply a lot of nitrogen. You supply plenty of potassium and phosphorus. Yeah, it's a big sector in Israel, the organic farming in avocado, but I've never heard of a post-harvest problem with it. Actually, if we want to open a discussion, what we see that might contribute to low quality post-harvest is anoxic conditions. If the soil is not drained well enough, it will lead to more rapid maturation of the fruits, and then it's ripening much faster on the shelf. And this is something I guess you don't want even in California, where you don't export the fruit.
Yeah, we have a couple more questions, but I think we need to move on to Rob, and I'll bring those other questions up when we have the open discussion.